Hello everyone. In this video, we are going to talk about logarithmic and exponential equations and change of base formula, section 11.7. So two things. Number one, change of base formula. How do we apply change of base formula to evaluate any given logarithms? Second thing, solving equations. The equation could be exponential equation or logarithmic equation. We start from change of base formula. This is the change of base formula. Logarithm with base a of b could be written as a quotient of two like basis logarithms. In the numerator, we have log with base c of b. In the denominator, we have log with base c of a. C here could be any number, as long as the number is positive, different from 1. Numerator, the anti in the numerator happen to be this number. The anti of the denominator is the original base. You see what I'm saying? This is the formula. Of course, we don't spend time to prove the formula. We only need to know what's the formula and how do we apply this formula. Any logarithm could be written as the quotient of two like basis logarithms. The base c could be any positive number different from 1. B goes on the top as the anti. A goes on the bottom as anti. So if c could be any positive real number different from 1, of course c could be e, the natural number e, right? Then we would have a numerator as a natural logarithm of b, denominator natural logarithm of a. And c could also be 10. If we choose the base as 10, the numerator would be common logarithm of b, denominator would be common logarithm of a. In previous video, I showed you how do you use the calculator to evaluate natural logarithm and common logarithm, right? So that we need to use that technique here as well. You wouldn't be able to find any other logarithms in a calculator. We could only, with the available calculator, we could only evaluate either common logarithm or natural logarithm. So what if you need to find the value for log with base 2 of 3? You wouldn't be able to evaluate by using the calculator directly. You have to do something. You have to apply the change of base formula. If you prefer a common logarithm, then you rewrite this logarithm as common logarithm of 3 over common logarithm of 2. And then you use the calculator to find the value. If you prefer natural logarithm, then you would have natural logarithm of 3 over natural logarithm of 2. So that's the purpose of learning a change of base formula here. Let's see example 1. Evaluate, round your answer to 4 decimal places. Number 1, evaluate logarithm with base 2 of 12. As I said, you are not able to find the result by using the calculator directly. You have to do something. You have to apply the change of base formula. Either common logarithm 12 over common logarithm 2. You see that 12 goes on the top, 2 goes on the bottom. Or you use the natural logarithm ln 12 over ln 2. Either way, you would have the same result. Let me show you. Numerator is ln 12, right? ln 12, close the parentheses, and divided by ln 2, close the parentheses. What do you have? You have 3.58. We need to keep 4 decimal places, so that's about equal to 3.5849. So that's 50 actually. 50. 5850. Keep 4 decimal places. Because the 5th digit is 6, we need to round it up. So what if we use a common logarithm? log 12 divided by log 2. You have the same thing, right? Yeah. Sometimes it depends on your calculator. You might have to use two more sets of parentheses, like what I used here. I use a parenthesis to frame the numerator, ln 12, and then divided by, I use the parenthesis to frame the denominator, ln 2. Same value, same thing. Number 2, log with base 4 of 100. We're going to apply the same procedure, right? Apply the change of base formula. Rewrite this logarithm either as a common logarithm of 100 over common logarithm of 4, or natural logarithm of 100 over natural logarithm of 4. Let's see what we have. We have common logarithm of 100, close the parentheses, divided by common logarithm of 4, close the parentheses. We have 3.3219. We round it down in this case. If we use natural logarithm, we have a natural logarithm of 100 divided by natural logarithm. Oops. So you see, we can, the two logarithms in the quotient must have the same base. If you use natural logarithm on the top, then the bottom has to be natural logarithm as well. 4. Close the parentheses. We have the same thing, right? Same result. That's how do we apply change of base formula. That's the first thing we need to learn in this section. Second thing, we are solving equations. Example 2. Solve for x. Round your answer to the 4 decimal places. Round to 4 decimal places. Let's see, number 1. Oh, example 2. Yeah, number 1 is 2 to the power of x equals 10. This equation is an exponential equation. We saw elementary exponential equation before. Both sides of the equation could be written as powers of the same base. However, this one not very easy. It is still possible to write both sides as the same as powers of same base, but not very obvious and not very easy. So we're going to apply a different way to handle it, okay? The way that we handle it is we're going to apply common logarithm. Preference, you want to use common logarithm or natural logarithm, should be okay. Either way should be okay. Solution. This is how we handle it. we are going to apply log common logarithm on both sides. Okay? And look at the left-hand side. What's the anti of the common logarithm? This is the anti, right? The anti is a power. Do you remember power rule? By the power rule, we could move x in front. X multiplied by log of 2 equals log of 10. Okay? So this is a number. So on the left, we have a number times x. If we divide both sides of the equation by the number log of 2, we would have x equals log of 10 over log of 2. For the calculator part, I would leave that for you to do the job, okay? By the way, what's the numerator? What is log 10? That's 1, by the way, okay? Because the base is 10, anti is 10. For a logarithm, if we have the base and anti are identical, the logarithm equals 1. So it's the reciprocal of common logarithm of 2. Yeah, we skip the evaluation part. Only solve for x. Number 2, we have another exponential equation. Is 4 to the power of x plus 2 equals 400. This is not elementary because it's not very straightforward to rewrite both sides as powers of the same base. So we're gonna do the thing that we just did earlier in previous example. We have the exponential equation now, and we apply either a common logarithm or natural logarithm. Since we did common logarithm earlier, this one I'm going to do the natural logarithm, ln. Remember, function is kind of like operator. We apply natural logarithm on the quantity on the left, and I apply natural logarithm on the quantity on the right also. So if I have an equation, if I treat the both sides of the equation the same way, then the equation would remain the same. Let's look at the left-hand side. Again, the left-hand side has anti 4 to the power of x plus 2. By the power rule, we are able to move the power in front as a coefficient. We move x plus 2 in front, we have ln 4. Right-hand side, ln 400. Remember, ln 4 is a number, is a value, is a number. If we divide both sides by ln 4, they cancel each other, right? Then we would have x plus 2 by itself on the left. And then on the right-hand side, we have ln 400 over ln 4. Minus 2 from both sides, we have x equals ln 400 all over ln 4 minus 2. Again, I leave this for you to evaluate using a calculator. One thing I want to point out is some students are pretty creative. This is wrong, by the way. They divide 404 and incorrectly get the result ln 100. They divide 400 by 4. That is wrong, okay? Please don't do that. We don't have any formulas like that. Number 3, ln x squared equals log with base 3 of 9. Let's see how do we solve this equation for x. Before I do anything, I notice both sides of the equation, both sides of the equation, the logarithm I can like transform a little. For example, the left-hand side, the anti is x squared. By the power rule, I could move the 2 exponent in front, rewrite the left-hand side as 2 times ln x. And on the right-hand side, I have 2 actually. Let me explain why. log with base 3 of 9, right? Base is 3, anti is 9. What's the connection between 3 and 9? We all know 9 is a perfect square. Is the square of 3, right? By the power rule, we could move 2 in front. We have 2 times log 3 of 3. What's the value of log with base 3 of 3? 1. If the base and the anti are identical, the value of the logarithm is 1. So we have 2 on the right-hand side. I explained it here. And divide both sides by 2. We don't have 2 anymore. Then we would have ln x equals 1, right? How do we continue from here? This is a logarithmic equation. How about let's convert it to equivalent exponential form. What's the base? Base is e. What's the log? Log is 1. What's the anti? Anti is x. So x equals e. Okay. Number 4. Given equation is 25 to the power of x squared minus 3. On the right, we have 5 to the power of x. You know, this equation actually is elementary exponential equation because we are able to rewrite both sides as the powers of the same base. I see 25, I see 5. 25 is the square of 5. So if I replace 25 with 5 square, the left-hand side, by the power rule, we would have 5 to the power of 2 times x squared minus 3. On the right, we have 5 to the power of x. So exponentiation equals another exponentiation. They have the same base. They should have the same exponent. So we equate the two exponents. 2 times x squared minus 3 equals x. We would have a simple quadratic equation. Distribute 2x squared minus 6 equals x. 2x squared minus x minus 6 equals 0. I distribute 2 times x squared, 2x squared, 2 times negative 3, negative 6. And then I move x over. Positive x becomes negative x on the left. So we are looking at a quadratic equation. How do we solve that? Do you remember the slide divide method? Slide divide method. Let's apply this method here. 2x squared minus x minus 6. Slide the coefficient to be with the common constant term. We have x squared minus x minus 12. Factor it. The two numbers are going to be negative 4, positive 3. Double check. Negative 4 times 3, negative 12. Negative 4 plus 3, negative 1. Yes. Divided by the original leading coefficient 2. Reduce x minus 2. 4 over 2 is 2. And x plus 3 over 2. We don't have to slide it back. You should have that in your note because we talked about this before. So the left-hand side is factored as x minus 2 times x plus 3 over 2. We have x either equals 2 or x equals negative 3 over 2. 2 is the opposite of negative 2. Negative 3 over 2 is the opposite of positive 3 over 2. The method we applied to solve this quadratic equation is called the slide divide method. We do not have to slide back. We talked about this before. If we are factoring, of course you have to slide back. But we are solving a quadratic equation. We could only we don't have to slide back. Only 2 steps, slide and divide. All right, so let's move forward. Number 5. The previous 4 problems are exponential equation. The last 2 are logarithmic equation. I hope I can finish this in this video. Seems like okay. The recording seems like okay. Number 5, ln x plus ln x squared equals 3. On the right hand side, I have 3 by itself. On the left, I have an addition of 2 like basis logarithms. They both have base e. By the product rule, I'm able to rewrite that equation as I'm able to rewrite the left-hand side as ln x times x squared, and that is ln x cubed, right? Could I move the 3 in front by the power rule? The anti here is a power. I could move the power 3 in front. I have 3 ln x equals 3. Divide both sides by 3. 3 is cancelled out. We have ln x equals 1. Converted to exponential form, e to the power 1 equals x, so x equals e. One thing we need to be very careful is when we solve a logarithmic equation, the last step is to check your result. It's mandatory, you have to, not optional. It's mandatory, you have to check your result. Bring it back. So we have the original equation is ln x plus ln x squared equals 3. So you plug in ln e here and ln e squared here. Ln e is 1. Base and anti-identical, so it's 1. We move to in front, ln e. Again, ln e is 1. So 2 times 1 is 2. 1 plus 2 equals 3. So we keep this solution. You can make a conclusion. The solution set of the original logarithmic equation is a set containing one solution only, which is E. Very important, I hope you can repeat the video. Number 6, log x minus 3 is a common logarithm because you don't see the base. Base is 10. Log x plus 2. We are going to solve this equation for x. What I'm going to do is firstly, I move the 2 common logarithms on the same side. Common logarithm of x minus 3 minus common logarithm of x plus 2 equals 2. I move negative 2 over. On the right hand side, we have positive 2. Okay? Yeah, I move the 2 common logarithms together on one side of the equation, then I can combine them or condense. Do you remember expanding and condensing? On the left, by the quotient rule, I'm able to condense the left-hand side as log base is 10. 1 logarithm. Numerator is x minus 3. Denominator is x plus 2 equals 2. So this is one simple logarithmic equation. If we convert the equation to exponential form, we have 10 to the power 2. The base is 10. Common logarithm. 10 to the power 2 equals x minus 3 over x plus 2. So actually we are solving a rational equation now. We have a rational equation. If we switch the both sides, we have x minus 3 over x plus 2 equals 100. Multiply both sides by x plus 2. Right-hand side multiplied by x plus 2. Left-hand side also multiplied by x plus 2. These two terms cancel each other. We would have x minus 3 on the left. We have 100 times x plus 2 on the right. It's a linear equation. X minus 3 distribute 100 times x, 100x. 100 times 2, 200. I move 100x over. I have a negative 100x. I move a negative 3 over. I have a positive 3. I move them around because I want to combine like terms. X minus 100x, negative 99x. 200 plus 3, 203. Divide both sides by negative 99. I have x equals negative 203 over 99. Turns out our proposed solution is a negative. What's the last step? Before you wrap up